Hello, hello students. Good afternoon. Uh, third article, third topic in unit number 3 is differentiation under the integral signs. There are two rules of DUIS, means differentiation under the integral sign. So what we do here, we differentiate the integrand under the integral sign. That's why this rule is called rule of differentiation under the integral sign. Now, this type of the integrals we use to evaluate certain improper integrals where it involves certain parameter. So the rule number 1, it is with the constant limits a and b. These are constant limits. Alpha is parameter. So this rule states that if f of alpha, if alpha is some parameter, we denote that integral by f of alpha, phi of alpha, or whatever it may be. With respect to x, it is given, then f dash alpha, df by d alpha, f dash means total derivative, is equal to a to b, dabba by dabba alpha of f of x alpha with respect to x, where a and b are constant limits and alpha is parameter. So let us see how to operate this rule for finding values of certain integrals by considering the constant to be parameter. So first example, evaluate or show that the integral 0 to 1 x raised to alpha minus 1 divided by log x into dx, this is equal to log of 1 plus alpha for alpha greater than or equal to 0. So we have to show this. Solution, we consider LHS integral as I 0 to 1 x raised to alpha minus 1 divided by log x with respect to x. Now, how to operate the first rule? 0 to 1. 0 and 1 are constant limits. 0 and 1 are constant limits. It is with respect to x, so alpha is the parameter. So I consider this as f of alpha, this integral, and using DUIS, first rule, using DUIS, f dash alpha, this is equal to 0 to 1 according to the rule dabba by dabba alpha x raised to alpha minus 1 upon log x with respect to x. So 0 to 1 with respect to alpha, partial derivative with respect to alpha, keeping x as a constant. So x raised to alpha into log x minus 0 divided by log x, that is what? The derivative with respect to alpha. Log x gets cancelled. Then f dash alpha means df by d alpha. It is 0 to 1 x raised to alpha with respect to x. Now we integrate this with respect to x. X raised to alpha plus 1 divided by alpha plus 1. Integration, limits are like 0 to 1. Upper limit minus lower limit. So it is 1. 1 raised to alpha 1 minus 0 means divided by alpha plus 1 and 0. So it is 1 upon alpha plus 1. This is f dash alpha. I call this is 2 and say the original integral, it is 1 over here, it is already designated. Now integrating with respect to alpha parameter. So it is integration of f dash alpha d alpha is equal to d alpha divided by alpha plus 1. So it is f of alpha, this is equal to integration log of 1 plus alpha or alpha plus 1 integration of 1 upon alpha plus 1 c plus constant c. So constant to be determined from the original integral 1 f of alpha. So how to determine this constant? You have to choose the value of alpha so as to become this integral convergent. Put alpha is equal to 0. If we put alpha is equal to 0, then x raised to 0, 1 minus 1, it is 0. So f of 0, this is equal to log of 1, 0 plus 1 plus c. So f of 0 is 0. F of 0 from here, it is 0. So log 1 is 0. So c is equal to 0. You are getting? And substituting this value in 3, we get f of alpha means the original integral. It is log of 1 plus alpha plus 0. And hence the value of this integral, it is log of 1 plus alpha. So this is the way we can apply this rule with constant limits to evaluate certain integrals where it involves a parameter. So let us see more examples on this. Second problem, show that integral 0 to infinity e raised to minus alpha x sin x upon x dx, this is equal to cot inverse of alpha, and hence show that 0 to infinity sin x upon x dx is equal to pi by 2. So here again alpha is the parameter. Solution, let alpha is parameter, integral given with respect to x. Let f of alpha or phi of alpha, the LHS side integral sin alpha x upon x into dx. So we use DUIS here, differentiating using DUIS first rule. With respect to alpha, f dash alpha, this is equal to 0 to infinity under the integral sign with respect to parameter e raised to minus alpha x sin x upon x into dx. So with respect to alpha, so this is constant, 0 to alpha, differentiation 0 to infinity. Derivative of this with respect to alpha is minus x sin x upon x into dx. X cancels, you are getting minus 0 to infinity e raised to minus alpha x into sin x into dx. So you have to integrate this using the formula integration of e to the power ax sin bx. This formula we are using, and this formula is e raised to x upon a square plus b square inside the bracket a sin bx minus b cos bx. This formula we are using and applying here. So a is minus alpha, b is 1. So I write down this as e raised to minus alpha x divided by a square plus b square means alpha square plus 1 inside the bracket. A means it is minus alpha sin x minus b cos x, and limits applied, it is 0 to infinity. So we apply the limits here. So see, e raised to minus infinity means 0. So 0 multiplied by whole expression is 0, minus plus here, lower limit So it is e raised to minus alpha x 0, 1 upon e raised to 0 is 1, 1 upon alpha square plus 1 inside the bracket, sine 0 is 0, cos 0 is 1. So you are getting this as this is equal to minus 1 upon alpha square plus 1. This is f dash of alpha. Now we integrate this normally. This is expression 1 and this is 2. Integrating. So if you integrate integration of f dash alpha d alpha, this is equal to minus d alpha upon alpha square plus 1. So integration of this is f of alpha. Integration, I take this minus tan inverse of alpha plus c. Again, we find the value of c, we choose parameter alpha from the original integral so as to become finite, and the value of alpha here we have to choose alpha is equal to infinity. If we choose alpha is equal to e raised to minus infinity, it is 0. 0 multiplied by the whole expression, it is 0. So f of infinity is 0 we are putting, and f of infinity, this is equal to minus tan inverse of infinity plus c. So this is 0 minus pi by 2 plus c, and c is equal to pi by 2. Put this value, c is equal to pi by 2, you are getting pi by minus tan inverse of alpha plus pi by 2. It is cot inverse of alpha, and that is the value of that integral. So this is the way we can just find the value of the integrals. We go for the next example. Show that 0 to infinity e raised to minus x minus e raised to minus b upon x into dx, this is equal to log of b upon a, where a is greater than 0, b is greater than 0. So consider LHS. Let here two parameters a and b, these are two parameters, so you have to choose one of them as a parameter, either a or b. So I take a as a parameter, so I denote this integral on left hand side as f of a 0 to infinity e raised to minus x minus e raised to minus bx upon x into dx. So a. So you can choose b as a parameter also, then we denote by f of b and so on. So it does not makes the difference there if you choose b as a parameter, because you are getting the same value here. Okay, so using DUIS first rule, because limits are constant. First rule, f dash a, this is equal to 0 to infinity dabba by dabba a of e raised to minus x minus e raised to minus bx upon x into dx. So this is equal to partial derivative with respect to a. If you choose parameter b, then partial derivative with respect to b. So here derivative of this with respect to a is e raised to minus x into minus x, and this is 0 divided by x, because x is constant, b is constant with respect to x. So this is, you are getting minus 0 to infinity e raised to minus x dx. This is equal to, we integrate this, minus e raised to minus a upon minus a. It is something like this. Limits 0 to infinity, minus minus plus here. So we apply the limits. So we got this as, this is equal to, we apply the limits, 1 upon a e raised to minus infinity minus e raised to 0. So you are getting minus 1 upon a, because this is 0, this is 1. So f dash a, we integrate this, this is 2 and this is 1. On integrating, integration f dash a dA with respect to parameter minus 1 upon a dA. So we integrate this. This is f of a and this is minus log a plus c. This is expression number 3. So we have to choose to find c. To find c, as said earlier, put a is equal to b in 1. So what is happening? See, if you put a is equal to b, then it is becoming 0 or some finite value. A is equal to b if you are putting, then it becomes 0 here. So this is f of b, this is equal to minus log b plus c. So this is 0, this is equal to minus log b plus c. So what is the value of c? C is equal to log b. If you substitute this value over here, you are getting the final answer. Here you are getting log b minus log a, that is log b upon a, which is required over here. So this is the problem number 3. Now we go for next example, that is problem number 4 here. So fourth example, show that the integral 0 to infinity e raised to minus x minus e raised to minus bx upon x into sec x into dx, this is equal to 1 by 2 log of a square plus 1 upon 2. Now see here, again only one parameter, so it is a square. Actually this is a e raised to minus ax, x sec x, it is 1 by 2 log of a square plus 1 by 2. Now here a is parameter, solution, a is parameter, so let LHS be f of a, it is 0 to infinity e raised to minus x minus e raised to minus x divided by x into sec x dx. A is parameter, limits constant, therefore we apply DUIS first rule, rule of constant limits. DUIS means differentiation under integral sign. So f dash a by the rule, or df by dA also you can write, df by dA, that is total derivative, here partial derivative, dabba by dabba a of e raised to minus x minus e raised to minus ax upon x sec x into dx. So it is something like this, 0 to infinity with respect to a, this is 0 minus e raised to minus x, derivative of e raised to minus x with respect to a is minus x divided by x into sec x into dx. So minus minus plus, here this x gets cancelled and you are getting this as 0 to infinity sec x at the numerator, it is e raised to minus x into cos x with respect to x. So I integrate this by the requisite formula, e raised to minus x divided by a square plus 1 inside the bracket minus a cos x plus sin x, and limits applied, it is 0 to infinity, limits applied 0 to infinity. So if you apply upper limit, this is equal to e raised to minus infinity, it is 0, lower limit you are getting 0 if you put 1 upon minus 1 upon a square plus 1, and here it is minus a cos 0 is 1 plus sin 0, it is 0, and bracket complete. So you are getting this as it is something like this. This is equal to f dash of a, it is a divided by a square plus 1. So it is expression number 2, this is expression 1. We integrating this, integrating. So what happens here? f of a you are getting on the left hand side, right hand side a divided by a square plus 1 with respect to a, and I just adjust 2 here, so it is 1 by 2. Differentiation of this is this, so log of a square plus 1 plus c, and this is f of a. So we again use to find c, use this, so you are getting it is c. From the original integral, put, in order to become 0, put a is equal to 1. A is equal to 1 if you are putting, then f of 1 would be 0. This is equal to half log of a square. A is equal to 1 means it is 2 plus c, and then c would be something minus 1 by 2 log of 2. So substitute this value in expression number 3. So you are getting your final answer, that is what required over here, c minus half log. If you take, it is a square plus 2 upon this. So this is the way you can apply the rule number 1 for differentiation under the integral sign. Is very useful for evaluating certain improper integrals if it is not possible to find value of that integral by traditional methods of integrations. Okay. Plus sin x, and limits applied, it is 0 to infinity. Limits applied 0 to infinity. So if you apply upper limit, this is equal to e raised to minus infinity, it is 0. Lower limit, you are getting 0 if you put 1 upon minus 1 upon a square plus 1, and here it is minus a cos 0 is 1 plus sin 0, it is 0, and bracket complete. So you are getting this as it is something like this. This is equal to f dash of a, it is a divided by a square plus 1. So it is expression number 2, this is expression 1. We integrating this, integrating. So what happens here? F of a you are getting on the left hand side, right hand side a divided by a square plus 1 with respect to a, and I just adjust 2 here, so it is 1 by 2. Differentiation of this is this, so log of a square plus 1 plus c, and this is f of a. So we again use to find c, use this, so you are getting it is c. From the original integral, put, in order to become 0, put a is equal to 1. A is equal to 1 if you are putting, then f of 1 would be 0. This is equal to half log of a square. A is equal to 1 means it is 2 plus c, and then c would be something minus 1 by 2 log of 2. So substitute this value in expression number 3. So you are getting your final answer, that is what required over here, c minus half log. If you take, it is a square plus 2 upon this. So this is the way you can apply the rule number 1 for differentiation under the integral sign. Is very useful for evaluating certain improper integrals if it is not possible to find value of that integral by traditional methods of integrations. Okay.